Yeah, it started.
So welcome everybody for the last episode of season 4 of the COMSOC video seminar. So we'll have two speakers today. We'll have first Jean Lainé and then Théo Delemazure. So Jean will first present his paper, Strategy-proofness with detectable lies. And this is a joint paper with Gilbert Lafont and Ramsey Sanver that we all know. Jean, the floor is yours.
Thank you, Vincent. Yeah, as you say, this is a joint work with Gilbert and Ramsey, but I'm delighted that Bill is around because we started actually, all this work started with a discussion involving Bill and Ramsey. And at that time, the title was slightly different. And then the title is the idea of Ramsey. So you may discuss whether it's an appropriate title or not. Later. So what I'm going to do in 20 minutes is just to make a very brief review of alternative concepts of strategy-proofness. Of course, I will devote most of my time to explain the title. The result will be very, very easy to describe. It's not very easy to prove, but this is a different thing. There is a funny corollary to this result. And then I will explain briefly how to generalize this concept of detectable lie, and I will conclude. So it's quite easy for me to present this because we are really in the typical standard social choice framework. So there is not much to say about this. You know, we have finite sets of alternatives and individuals. Each individual has a linear order as preference. So no indifference. And we are interested in single choice situations. So we're interested in social choice functions. We select exactly one alternatives from the set A profile. We all know what it means. And of course, since I'm going to talk about strategy-proofness, then the classical way to talk about this is to introduce pivotal situations. So you see a triple, there is I with a voter. Let's talk about a voter I, a profile P, and at this profile P, some alternative A is chosen, and then this voter I changes a preference to Q, and by doing so, the outcome changes from A to B, okay? We can say, just to make it brief, that when I is changing a preference from PI to Q, then this is a lie. Okay, whatever it means. So basically, this function can be manipulated or is manipulable if there is pivotal situations where some voter can or has some incentive to lie, because he or she prefers the outcome that the lie allows to enforce. Okay, so the starting point is really the basic one. We know that as far as we impose that F is onto, and as far as there are more than two alternatives, then opposing strategy-proofness resumes to dictatorship. Okay. Now, of course, the first thing we have in mind when we want to overcome this problem is to restrict preferences. There is a huge set of work on this, and I'm not going to describe it because it's not really what we do. We can also overcome the problem by changing the setting, and instead of choosing a single alternative, then we can choose sets of alternatives as irresolute outcomes. And in that case, well, there are some work showing that we can somehow escape by somehow restricting preferences, because when you choose sets, basically, you have to restrict preferences. Maybe closer to what we do is directly weakening strategy-proofness. So for instance, there are some work where we assume that people have limited information about other preferences, okay? So for instance, suppose that all the information that you have is the following. You know how many people vote for A against B. You have this number. And you have such a number for each pair of alternatives, okay? but you don't know who thinks what. Well, in that case, should you lie or not depends on your attitude regarding this information. For instance, if you are conservative, and if you say whatever the profile which is compatible with these figures, I have some incentive to lie, then you lie, okay? But if there is exactly one alternative, which is one situation which is compatible with this information in which I don't have any incentive to lie, I will not. And of course, if you have this conservative view, then you show that some non-dictatorial choice function becomes, in that sense, non-manifold. You have also another approach which is related to achieving minimal gain from lie. Personally, I don't really like an approach where the benefit from a manipulation is measured by the rank. This is a kind of important limit to this approach, because I don't see whether moving from my third to my second is a big or a small jump. Well, it may depend on the situation and on people. Well, anyway, this is an approach. Another approach is limiting the type of lie that you can make. For instance, Sato introduces a concept where people can lie only by switching positions of two adjacent choices in their ranking, okay? And actually he shows that it doesn't change really the impossibility results, but this is an approach. And what we do is basically kind of a mix between what I just described, limiting the scope, limiting the possibility of lies, and also considering the information that people have about others. So to be more precise about what we have in mind, here is the key assumption. We assume that each voter perfectly recognizes whether a preference is carried out by someone else. Right? So to be clear, if my preference is Q, and if you announce that your preference is Q also, then I can say that you are correct. This is actually your preference or not, right? This is all I can do. So I can partition the set of voters into two sets. The first is those who have or pretend to have my preference, and the others. Okay. So I can detect whether there is a lie only if this lie is made by pretending that the preference is mine. There are some situations where we can justify this information. For instance, the first discussion we had with Ramsey was about this. Ramsey said something like, we were going to a meeting, I remember, and he said, should I pretend I'm French? So I said, yeah, but be careful, because I know that you are not. So I can announce that you are not French. And he said, would you do so? And I just said no, because I would be very honored if you were becoming French. So I will certainly not say that you are not French. So it's beneficial to me if you pretend that you're French, okay? So this has to do with some group identification, if you wish. There is maybe something which is closer to the idea, which is suppose that instead of voting by yourself, you can delegate your vote. So maybe you can manipulate by delegating your vote, and you nominate somebody to vote on your behalf, and this person may or may not accept this delegation in case where voting on your behalf is not beneficial to him, right? So this is the idea. And I think that having vote delegation in mind is the best way. Clemens has a clarification question.
Yes. It seems, well, okay, so I'm not understanding exactly what the assumption is. There are, I think, two possibilities. And the one that I would think of is that I know those people whose true preference is as my true preference.
Yeah.
But that would entail that I could also detect someone who has my preference but pretends another preference, right? So as I read your slide, it looks as if I can only detect if someone pretends to have my preference, then I can detect whether this is true or not. But it would seem natural to me that it should also work the other way around, right? If someone who has my preference claims to have another preference, I should be able to detect that as well.
Which is not what we assume.
Okay, very good.
Okay, but this is a very good point. Thank you. So the key idea is that in this informational setting, then this manipulation can be detected by a subgroup of people. This is what I described. But will they exert this possibility? Well, yes or no, depending on whether they gain themselves or not from this slide. Okay. So my manipulation can be recognized as such only by those who first can detect it and second would be harmed by this manipulation, right? And this leads to the following definition of what I call safe manipulation. So I mean safe manipulation, having in mind that the manipulation is safe if it cannot be reported as such, right? Well, go back to this pivotal situation, and then if B is the new outcome and A is the old outcome, then there will be no reporting if, as I said before, I myself benefit from moving from A to B, and all the people with Q preference also benefit from this change from A to B. And of course, the strategy-proofness with detectable lies holds if there is no possible safe manipulation. Okay? Right. So it's interesting to see that basically this concept of strategy-proofness with detectable lie is equivalent to say this choice function is either non-manipulable or manipulable in both directions. Okay? Why in both directions? Well, look at, for instance, these brackets. BA is in PI means that B is above A in PI. So there is some interesting manipulation there for I. And also AB is in Q means that A is above B for Q. So if the starting point is a profile where my preference is Q, then I still have incentive to manipulate by pretending that my preference is PI. So you see that both ways entail some possible manipulation, right? I will go back very briefly at the end of my talk about this. Right, okay. So the result is very simple. If there are at least three alternatives and if you impose surjectivity, then you'll find that strategy-proofness with detectable lie holds even only if you have either dictatorship or anti-dictatorship. That's it. So basically, restricting manipulation in the way we do does not really allow to escape from the given satisfy theorem. The proof is really pretty boring and long. So it's not really important here, especially in 20 minutes. The corollary is the following. You all know what IIA is. So in the context of choice function, if two profiles agree on two choices A and B, and if we choose A at the first, then we cannot choose B at the second. Okay? And it's very well known that if you combine this, for instance, with Pareto, then you will get a dictatorship. And also you have a Wilson type theorem that if you combine this IA with ontoness, then you have dictatorship or anti-dictatorship. Okay. At first sight, you don't see why I'm talking about IA here, but it turns out that our concept equivalent to this weakening of IA, which is of course weak IA here, which is exactly IA, but in restriction to profiles which are different only on one order. Okay? The first IA is for any two profiles agreeing on A and B. The second is for any two profiles that differ only on one single alternative, then the property holds. And it's rather easy to show that strategy-proofness with detectable lies is equivalent to this weak concept of IA. So, of course, it turns out that as a corollary, IA and weak IA are the same. So we can restate everything with this weakening of IA. This is not the major contribution of the paper, but this is, moving around. This is something which is maybe worth being said. Okay, so this is it. I mean, this is really what we do as a main result. There is a way to generalize this, which is instead of, being able to detect a lie with Q only if my preference is Q, I could detect a lie with Q if I share the same top in my preference than Q, right? For instance, if you pretend that your favorite candidate for the next election in France is Marine Le Pen, because your order put Marine Le Pen first, maybe all people who think that Marine Le Pen is the best are able to say, no, you're not honest, this is not what you think, right? That's a way to enlarge the population which is able to detect a lie. And of course, you can also generalize further, saying, okay, instead of taking just the first, why not taking the first K, right? So all the people sharing the same first K, the K first best choices in their preference as in Q, will be able to say that Q is a lie or not. Right. So we have a range of concept of strategy-proofness with detectable lies according to the population of people who are able to detect the lie, and this population is parameterized by the proximity or similarity between their preference and the one I'm using as a lie. And actually, not entering into the details, what we find is that if you generalize SPDL in that way, you find non-dictatorial choice function, which turns to be SPDL. But it's not really interesting. Why? Well, for this reason, the last line, if you consider, again, ontoness, one SPDL, remember, you detect a lie only if your top is the same as the top of Q, and if you combine this with simple monotonicity, which is if A is chosen and if A becomes more popular in the electorate, that A remains chosen, which is a basic property, then you're back to dictatorship. So it means that if you generalize SPDL as we do, you will have non-dictatorial social choice function moving on stage, but none of them will have what I think being a minimal property that is desirable for social choice function. So you will have only weird or exotic function that allows to escape from the given status weight theorem. So this is not really interesting. So this is still a negative result. But what I would like to say, just to conclude, is that finally, if you look at the standard strategy-proofness, we all know what it is. As I said before, if you look at SPDL, this is strategy-proofness or manipulation in both directions. Right? Remember here that if you have safe manipulation, then those two, A and B, should be ranked the same in PI and Q. Right? So if you don't want to have safe manipulation, they should be opposite. So it means manipulation in both directions. And what Bill and Ramsey did some time ago was considering what they call one-way monotonicity, which is basically a weakening of strategy-proofness, which says either a function is non-manipulable or it's manipulable only in one direction, right? So in some sense, and this was not the original intention, we complete the picture by considering both directions instead of one direction. And Ramsey and Bill showed that well, if you introduce one-way monotonicity in the picture, then you have appealing social choice function which turn to be one-way monotonic. Okay, they are not strategy proof, but at least there is one situation among the two directions in which they cannot be manipulated. And we get, with our concept, drastically different results because we somehow don't escape from the impossibility of given status weight. Okay, now what we are polishing at the moment are a few additional things about do we keep the same message if we choose set? Do we keep the same message under some preference restrictions? And for the moment, the only thing that it seems to be difficult to do is to characterize the class of choice functions which are on 2 and 1 SPDL. This is a technical exercise, which is, I must say, pretty boring, but it's even more boring because we know that, as I said before, the class of function that we are going to get contains no interesting element. So this is really for sake of completeness that we do this. And I spoke for about 22 minutes, so I should stop here.
Thank you very much, Jean. So we can unmute our microphone and applause. So you can perhaps unshare your document, and we don't have a lot of questions except a comment by Bill, but you already mentioned that there's a link between one-way monotonicity, so I don't think you have anything else to add, Bill.
No, my timing was perfect. Right after I asked the question, he answered it.
Okay.
We didn't talk before, Bill, but I'm happy to see you.
I'll see you soon.
Yeah, true.
Is there any other question? I think it was rather clear.
Clemens is... Oh.
Yes.
Clemens, where are you, Clemens?
I mean a very general comment that is not very original, because you may have expected that when you generalize the framework and you allow that lies become detectable, then of course the game, so to speak, right, that voters play becomes even more complex, right? Because then you have to consider which lie is optimal when some are detectable, and the other persons, right, the other players have to decide whether they want to reveal that this was a lie or whether it's in their best strategic interest not to reveal that others have lied. Is this, I mean, it makes things much more complex in some way. So it's, yeah, I mean I think it's interesting. It's an interesting idea that I agree that this may happen, that I have the strong suspicion that others lie in their preference reports, but it makes things extremely complex, I would say.
And the game is not formalized, right? This is
That's right. Yes.
but you're right. I mean, but I keep in mind your comment before, which is because this is a way to introduce partial detection, right? Maybe there are some others, and of course, the symmetry that you have in mind also makes sense. But so maybe we should think about stories where there is a clear-cut difference between the two, and symmetry should not be as much as the one you describe. And for the moment, I don't have an example in mind, because, for instance, if you say, well, my story of Ramsey being French or not, well, of course, if Ramsey pretends that he's maybe Croatian, I don't speak Croatian, so I may not be able to say that he's lying. Only when he speaks French, that since he's making exactly one mistake in 2 million sentences, then maybe with assumptions I can detect that he's not really French, but this is very rare. So I'm not sure it's even a good example in case of Ramsey. But, this is a story of language, which might be a way to illustrate that we may have some asymmetry between those situations. But you're right, the game, in fact, which is behind, may be extremely complicated and maybe interesting to analyze. Yeah, in some specific context at least. Yeah.
All right. Thanks.
You're only considering strict ordering. At least could you have a different picture if you allow for abstention, that is going from complete indifference to something else, or pretending I'm
well, to be honest with all
I'm
you,
thinking of scoring runoff, we are susceptible to abstention paradox.
Yeah. I mean, about moving to weak orders, for instance. Of course, there is a veto in the crowd. Gilbert is a vetoer, and he said never touch indifference. I mean, okay. So we didn't start thinking about it, to be honest. Yeah, but they may play a role, as usual. Yeah, you're right.
So if there's no other question, we will move to another voting mode.
Very last thing, Vincent, sorry to cut. I really have to apologize, because at 15 to 4, I will really oblige to leave because of this meeting. And again, thanks to Théo for having accepted to switch our presentations.
No problem.
So we'll be back in 10 minutes after the break to know whether we can characterize the French system or others with indifference voters. See you in 10 minutes. Okay. So perhaps, yeah, I think everybody's back. Even a few more people are here even. So Théo, I will ask you to share your document. And Nishag, as soon as we're ready for recording, tell me.
Yeah, I already resumed.
Okay. So our next speaker, the last speaker of the season. So I told previously to Théo that we're waiting for a cliffhanger. We're waiting for a cliffhanger at the end of the season. So I hope we'll have a cliffhanger. So the next speaker is a joint paper with Dominic, generalizing instant runoff voting to weak orders. And Théo, the floor is yours.
Thank you very much for the introduction and for inviting me to the seminar. So yeah, I'm going to present this paper, generalizing instant runoff voting to weak orders, which is joint work with my co-supervisor, Dominic Peters, who's also in LAMSAT. And we're here in the setting of single winner voting. So the classical setting, you have rankings of n voters over m candidates. So today our candidate will be named Anne, Bob, Cora, and Dan. And let's say you have this kind of profile. with like 10 voters having this ranking. We want to find a single winning candidate. For this, we use a voting rule. And today we are focusing on one specific voting rule, instant runoff voting. So you're probably familiar with this rule, so I will explain it very quickly. Basically, you associate to each candidate its plurality score. So the number of times it appears first in a ranking, and you successively eliminate the candidate with the lowest score. So for instance, here you eliminate Cora. So when Cora was first, Anne becomes the first one. So her scores increases. And you eliminate now Dan, who has the lowest score, and Anne is the winner of the election. So this rule is called instant runoff voting and is not an uncommon rule because it's actually in use either this single winner version or its multi-winner equivalent in various countries. So I put some example of countries that use either single winner or multi-winner or both. And it's promoted by different associations. For instance, Fair Votes in the US or Electoral Reform Society in the UK that are both pushing for the use of IRV instead of plurality or plurality with runoff. Okay, but the question we will ask ourselves is, what if we allow weak orders in the instant runoff voting rule? So what I mean by weak orders is instead of having a full ranking like this, you can also have ties between candidates and have several candidates with the same rank. So for instance, you can say, I really like Bob, then Cora second, and I'm indifferent between the two other. Or I really like Bob, I really hate Han, and I'm indifferent between Cora and Dan. Or you can also have approval ballots and say, I approve all of these candidates, Cora, Bob, and Dan, and I disapprove Anne. So all of these are valid weak orders. And the question is also, why should we use weak orders and not stay to rankings? And there are several good reasons for this. Let's focus on one, which is invalid ballots. And for this, we will look at an actual election using IRV for the mayor election in San Francisco. And the voters, they had this small ballots in which, so it's a grid. And for each candidate, they have to put a cross or a dot for the rank they want to give this candidate. And these two ballots here, they are invalid because they are weak orders. So they were not taken into account in the vote. For instance, this one, this voter put two candidates for the first rank, and then it's a ranking. And this voter even did an approval ballot with 3 candidates with rank 1 and 3 candidates with rank 2. So these two ballots are invalid, but they are weak order, so they could be valid in theory if we used a method with weak order. And if we look at the distribution of the proportion of invalid ballots in San Francisco, because they are weak orders, we have this very nice colorful map. I mean, it's not really meaningful if you're not familiar with San Francisco. So, but if we compare it to the distribution of the median household income of each precinct, what we observe is that there is a negative correlation between the proportion of weak orders ballots in the precinct and the median household income. So not taking into account this weak orders ballots, you kind of put a bias against the poorer precinct. So fewer invalid ballots is one argument, but you can also say that it's less cognitive effort because you don't have to rank everyone, especially if you are really indifferent between two candidates. You can express it with your weak order. That's why it's more expressive than only allowing rankings. And it also mitigates some issues of IRVs. For instance, favorite betrayal is often used against IRV and can be mitigated by using weak orders instead of complete orders. And finally, these weak orders, and especially with the rule I'm going to present later, are a good compromise between full ranking and using instant runoff voting and approval ballots and using approval voting. And you can, so if you like approval voting, you can do approval ballots. Like everyone can do whatever they prefer. And the question of this paper, the real question of this paper is, okay, now that you convinced that it's reasonable to generalize IRV to weak orders. What is the correct way to generalize IRV to weak orders? And there are actually two natural generalization that I'm going to present. And then we're going to see with axiomatic analysis and experimental analysis, which one is probably better. So the first natural generalization of IRV is what we called approval instant random voting. And it's very simple to understand. So it works the same as IRV, but now you're giving 1 point to all candidates that are in the top indifference class of each voter. So the score is still the plurality score or the approval score in some sense. The score of Cora is the number of times she appears first in a ranking, so 10 plus 6. The score of Bob is 10 because he appears 10 times first, and etc. And so you eliminate the candidate with the lowest score. Here it's Anne, which changed the orders. And now the candidate with the lowest score is Dan, and Bob is the winner of the election. So that's approval instant random voting. The second method you can use is split instant random voting. And it's actually what's in use in the few places that actually implement weak orders with instant random voting. And that's like university councils, I think. So split instant random voting, how does it work? The idea is that each voter, they can give 1 full point, but if they have several candidates in their top indifference class, they have to divide this full point between all of them. So for instance, these voters, they put both Bob and Cora first, so they have to give half a point to Bob and half a point to Cora, which is why Bob will get 5 points because he gets half a point for from the 10 voters, and Cora will get 11. And so now Bob is the first candidate to be eliminated. Even though with approval IRV, he was the winner. And now we have basically a full ranking profile, so we can just run IRV and Cora is the winner. So with these two rules, we had different winners. And these rules, we can put them in a large family of rules that we called elimination sequence rule, sorry, that are not restricted to generalization of IRV, but any elimination rule that is based on scoring vector. So let me explain quickly. For each order type, we will associate a scoring vector. So I will focus on the top right order type. So this one with Bob, Cora, and Dan, and Anne. This order type is the order type 1, 1, 2, because you have 1 candidate first, 1 candidate second, and 2 candidates in the third indifference class. And it will be associated to this scoring vector with so this one. And this means that every time we will encounter this order type, whatever the candidates inside are, we'll give them the amount of points that is given by the scoring vector. Then we will sum the point of each candidate to get the score of the candidate, and we eliminate the candidate with the lowest score. And we repeat until 1 candidate remains. Okay, to make it more clear, I will show some examples. For instance, approval IRV. We always give 1 point to the candidates, to all candidates in the top indifference class. So, and 0 points to all the other candidates. So it's a plurality vector. So what's interesting is to look at the last weak orders here, because all of Cora, Bob, and Dan, they each get 1 point, even though there are 3 in the top indifference class. And that's the main difference with split IRV, for which they will get only 1/3 of a point, because that's the weak order 3, 1, order type with 3, 1. So because there are 3 here, they get 1/3 of a point each. But for all the other, Bob is the only one in the top indifference class, so he gets 1 full point. And in this family, you also have rules that are not generalization of IRV. For instance, you can generalize Baldwin, which instead of the plurality vector, you use the Borda scoring vector, and you can do some interesting scoring vectors for weak orders. But that's not the topic. It's just to show that it's not restricted to instant random voting generalization. So now how to know which of approval IRV or split IRV we should use in practice. We can do first an axiomatic analysis. The first axiom I will discuss is independence of clones. I think most of you are familiar with it, but I will explain very quickly. So I will explain first for rankings. We have a profile of full rankings. And if, let's say, Anne is the winner with some voting rule in this profile, well, if we clone one candidate, if we add a clone of Bob called Bobby, then Anne should remain the winner. And Bobby is a clone of Bob if they always appear next to each other in every ranking, like here. And it also works in the other way. So if Anne is the winner in this profile with Bob and Bobby, if we remove a clone, then Anne should remain the winner. Okay. And it's known that instant runoff voting satisfies this property independence of clones. And it's one of these main characteristics. Now the question is, how do we generalize the notion of clones to weak order? So in our paper, we use, I think, the classical notion for weak order. So Bob and Bobby are still clones if they are next to each other in the ranking, but alone in their bundle, like here, in their indifference class, sorry. They also are clone if they are together in an indifference class, and they can share it with other candidates, but they are not clones if they are next to each other and one of them is sharing his indifference class with a non-clone. So for instance, Anne is in the same indifference class as Bobby. So if there is this order in the profile, Bob and Bobby cannot be clones. So that's how we generalize clones to weak orders. And if we use this generalization, we showed in our papers that approval IRV satisfies independence of clones and split IRV fails independence of clones. And to see why split fails it, we have a very simple example, which is here. So using split, here, these voters, they will give half a point to Anne and half a point to Bob, because there is both Anne and Bob in the top indifference class. So Anne will get 4.5, Bob 6.5, and Cora 4. So Cora is eliminated first, and Anne is the winner of the election. But Bob really wants to win, so he called his brother Bobby, him again. And now, so Bob and Bobby, they are clones, so they are always together. So it's possible by the definition in the same indifference class. And because of this, now Anne, Bobby, and Bob, they each get 1/3 of a point from this 9 voter. So instead of having 4.5, Anne has now scored 3, while Cora and Bob and Bobby all have a score 4. So Anne is the first to be eliminated, and either Bob or Bobby wins the election. So split is not independent of clones. It's 1 point for approval already. Approval IRV. The second axiom I want to discuss is also a very natural property. It says that, so it's respecting cohesive majorities, and it says when you look at it for full ranking, profile of full ranking, it says that if more than half of the voters agree on one candidate, agrees that put one candidate first, then this candidate should be the winner. So for instance here, 51% of the voter put Anne first, so Anne should be the winner of the election. That's because of respecting cohesive majorities. And instant runoff voting satisfies this axiom. Okay, how do we generalize it to weak orders? So we say this time that if more than half of the voter put one candidate first, so for instance here, Anne is put first by 51% of the voter, then the winner should be this candidate or any candidate that is put in the top indifference class of this 51% of voters. So here Bob, because he's also put first by this 47% who put Anne first, can also be a winner, and the rule will still respect cohesive majorities. So if you have a cohesive majority that puts the same candidate first, at least one of them should be satisfied, at least the winner should be in the top indifference class of at least one of these voters. And actually here, it actually makes sense that Bob is the winner instead of Anne, because only 4% prefer Anne to Bob, while 49% prefer Bob to Anne. And again, approval IRV respect cohesive majorities, split IRV fails cohesive majority. It's 2 points for approval IRV. And if you're familiar with C2 rules, well, no C2 rules respect cohesive majorities when you extend them to weak orders. Okay, and this leads us to our first characterization of approval IRV, which is the only elimination sequence rule. So not only among generalization of IRV, but among the whole family of elimination sequence rule that satisfies these two characteristics axioms of IRV. I mean, the generalization of these axioms. So it satisfies independence of clones and respect cohesive majorities. Okay, so now a third axiom, which is indifference monotonicity. And it might sound surprising because instant runoff voting is famously known to fail like any kind of monotonicity. But if we weaken it enough with weak orders, it can actually be satisfied by our rule approval IRV. Okay, so let's say that I will explain the axiom with an example again. Let's say that we have this profile of weak orders and Anne is the winner. Monotonicity says that if I put Anne, if Anne is ranked higher by one voter, Anne should remain the winner. So for instance, if in the second ranking I put Anne, who was here with Bob, so that instead of being after Bob, she's now sharing the indifference class of Bob, there is a tie. Well, Anne should remain the winner. So this is allowed by this notion of indifference monotonicity because you create an indifference. However, you cannot switch Anne and Bob. So if you increase the rank of Anne, you cannot, I mean, the position of Anne, you cannot decrease at the same time the support of Bob. And similarly, you cannot move Anne from this indifference class with Cora to this indifference class with Dan, because you need Anne to be alone in his indifference class before you apply the monotonicity notion. So this one is not allowed either. So it's a very, very weak notions and not a lot of improvements are allowed. But even with this weak notion, only approval IRV satisfies it, while split fails it. And it's already 3 points for approval IRV and still 0 for split. And this gives us our second characterization, which says that approval IRV is the only elimination sequence rule that generalize IRV, so it's equivalent to IRV on linear profiles, and it satisfies indifference monotonicity. So even with this very weak notion of monotonicity, we can characterize this generalization among all generalizations of IRV, restricted, of course, to elimination sequence rule. Okay, so that's it for the axiomatic analysis, in which we found two nice characterizations of approval IRV. Let's now go into the experimental analysis. And for experiments, we use various data sets. We use real data and synthetic data. What's interesting with real data is that it's taken from elections that are actually using instant runoff voting or the multi-winner version single transferable voting. So in Dublin or in a French experiment that was done in parallel of the presidential elections. And we also have synthetic data with several models, but I will focus on Euclidean in the next slides. But all of these data sets, I only give full rankings. What we want is weak orders. So we need a method to turn full ranking into weak orders. The first method is only for Euclidean datasets. So in Euclidean models, each voter, for instance, V here is the voters, and each candidate, so for instance, A, B, C, D, E, they all have positions in the plane or in the line. And we will create a weak order using a parameter R, which will be the radius of the circles. And everything in the first circle of radius R is in the same indifference class. Everything in the second radius between R and 2R will be in the second indifference class, etc. So for instance, here, the weak order will be A, B together. There is a tie between A and B, then C, D, then E. So this is only for Euclidean. So we need a method for all the other data sets. And this is the second method that we called coin flipped, and it's very simple. Basically, you have a coin with probability P, you flip it for every consecutive candidate, and every time it's successful, you create a tie between the two candidates, and this gives you a weak order. So this is the second method. And in both of these methods, they have a parameter that is somehow like between 0 and 1. And for 0, split IRV and approval IRV are equivalent because everything is linear order. And if the parameter is 1 or is very high, everything is a tie, so it's not very interesting. And so in these figures, for instance, the parameters vary between 0 and 1. So yeah, this is the x-axis represents the parameter. And in this first set of figures, the y-axis is the distortion. So to go very quickly, the distortion is an utilitarian metric that measure if the winning candidate, how far it is from the optimal candidate in terms of utility or cost in this case, because it's CLIDEM. And most importantly, the lower the better. So here, approval IRV is lower than split IRV, like the line, which means that in average, approval IRV gives a winning candidate with a lower distortion for every value of the parameter. And so in a utilitarian way, it's better. And if we look at in which percent of the profiles generated for each parameter does each rule return the candidate with the better distortion, we see that it's more frequent that approval IRV returns the candidate with a better distortion than split IRV. And in a lot of cases, they return the same candidates, of course, especially when it's close to 0 or it's close to 1. Okay. What we also noticed in this experiment is that the approval IRV winner in average has higher border score. So yeah, his border score, if we look at the original profile with full ranking, the border score of the candidate selected by approval IRV will be higher and is more often a Condorcet winner. Here it's only the figure for the border score. And here this time the higher, the better in some sense, but it depends if you consider the border score to be a good utilitarian metric. And in the other hand, split IRV, the winner of split IRV will be closer to the IRV winner of the original profile before we do the weakening. So this kind of gives the intuition that approval IRV will tend more to the consensus on the approval side, while split IRV is still close to IRV. I mean, there are some explanations to this, but I don't have time to. Right, it's in the full paper. And this observation is not only on the few data sets we tried, but if we look at the map of election, we observe the same results in most data sets, not all of them. So here it's again the difference of border score between the two rules, and in blue, if the dot is blue, it means that in average, approval IRV returns the candidate with higher border score, and most of the map is blue. Okay, so to conclude, in this paper and this talk, we focused on generalization of IRV to weak orders, and specifically with elimination scoring based rule. And we showed with axiomatic, so with two characterizations, that approval IRV is the most natural generalization of IRV if we want to keep its core properties. And the experiments showed that approval IRV seems to be somehow better than split IRV. In the paper, we also define the multi-winner version approval STV and show that it satisfies generalized PSC for those who are familiar with it, while split STV does not. And we also considered paths for further works, that's the last line. And so thanks a lot for your attention. I hope I did not take too much time. And if you have questions that are not answered yet by my co-author in the chat, I'm happy to answer.
Thank you. Thank you, Théo. People, we can unmute to make a round of applauses or just put an icon in the on the image. Okay, so we have a round. We have already a round of questions, I think, in the chat or comments. Blah blah blah. Just let me check where do we start? Blah blah. Sorry.
I think starting with your question, Vincent, they haven't been answered.
Okay.
How
My answer is, how do you handle ties? A very basic, but
yeah, it's a good question.
in
How
the
do we
elimination process, how do you? It's a basic question for elimination process, but at some point you may have a tie. Who do you eliminate?
I think I mean, for the characterization, we considered worst case scenario.
Okay, so
But yeah, we use the parallel universe tie breaking method.
okay. Okay, sorry. There was a question. I'm so sorry, I'm a bit lost. Perhaps Clemens, while I'm checking, you can ask your question.
Yes, hopefully it's not already contained in the chat. So I think I have two questions. One is related to Nizark's point. Is it really okay to interpret these ballots that you have shown to us as expressing indifference? I mean, if these are mistakes and not indifference.
Yeah.
Right? So that's one point. And I think Nizark already asked, I mean, how many mistakes in the other directions were there? But I think you answered that. That's one point. But I think more important is the following. I wouldn't be worried about forcing voters who report weak orders to tell them, listen, I want to have a clear decision. You cannot express indifferences with my voting system. I'm very sorry. Please, if you have an indifference, resolve it. I would tend to think that this is possible and doable, in contrast to voters who say, I cannot compare these two candidates. Then it is completely different, right? If I want to make a difference between incomparability and indifference. These seem to be very distinct things in such voting situations. So I would rather want to see a version of instant runoff voting which allows for partial orders than weak orders. I would find that more important. But okay, that's an unfair comment. I'm sorry.
No. It's thanks for the comments. So with partial order, so it's even you allow even more kind of orders, right?
Yes, correct.
Yeah.
But strict partial orders. Let's say strict partial orders, right? I force them, if they decide, they must decide for one or the other, but they have the possibility to refrain from comparing. And then, of course, I think the picture changes. And okay, anyway, so it was very general comment, sorry.
Okay. And for the comment about the ballots, yeah,
Yes.
it's possible that maybe they interpreted it as giving scores and not rank, and maybe that's why they gave this. I mean, we don't know for sure that it's they have indifference, but it can be interpreted like this. It's like,
but I think Dominic had some answer to Nizark's question about how many invalid ballots there were in this other way, even more invalid ballots. No, you didn't?
yeah, you answered. So you mean
In the chat?
in candidates that get several rank?
Exactly. Candidates that get several ranks, which is also invalid.
Yeah, yeah, he says he didn't have a, yeah, it's this one are like really invalid. We cannot do anything for that.
So Bill had a question about manipulation.
Yes, instead of asking the question I actually asked, let me ask the question that lies behind it, which is that sometimes there's an attack on approval voting, a naive attack, I would call it, that says it's unfair because people who approve of more candidates get more influence over the outcome. And of course, the response to that is, but then they disapprove of fewer, and you can make a dual argument that points in the opposite direction. Do you have anything like that here that would justify your approval version versus the split version? Because the split version is like the argument of people who say that in approval voting, if you approve of several, you shouldn't get 1 point each. You should split the points to be more fair. So do you have an argument that this is somehow more fair, or doesn't represent added influence for the people who have a large top difference class?
Oh, does it advantage them? So I think that's one of the further work, but like, because I don't think it will I mean, it's like in approval, it doesn't really advantage, but it's one of the key question is how to explain, how to convince that it will not
Exactly, that's my
advantage.
question, really. How to convince
Yeah.
people that you're not giving extra influence to approval of a bunch of people at the top.
Yeah, so that's one of the, I mean, we fought and we like, yeah, further work, how to convince them it's not getting an advantage, and it's not trivial to explain, I guess. But I think we did also some experiments, I mean, preliminary experiments on strategy-proofness or things like this, but it was not very convincing, so it's not on the paper. Like, we didn't see much difference between the two rules, and this could be used to convince them that it's you cannot do very different things.
Okay. Lirsa got a question?
Yeah, so great talk, by the way, Theo.
Thanks.
From the experiments, it wasn't surprising to see that approval does better than split for distortion, just because kind of split sounds too extreme. If I put 3 candidates in the first place and they just get 1/3, but I feel like the optimal thing could be somewhere in between these two. So have you considered maybe other type of scoring functions where you give f of k points if there are k people in the indifference class, where f of k is somewhere between 1 and 1/k?
Actually, I think we maybe Dominic will say I'm saying mistake, but I think we didn't, at least in experiments. I don't remember we did. We used rules like this. We only compared split and approval, but it will be like it will be interesting to see if it can be outperformed by something like this. So your rule is
Yes, say 1/√k if there
okay.
are k people in the top class.
Okay. Well, that will be interesting to investigate and see. That's also, yeah, one of the further work is to look at the distortion, not average distortion, but like worst case distortion of this. But yeah, that will be, thanks for the
Rob,
would say.
Rob, are you here?
Hi, can you hear me?
Yes.
Yeah.
Okay, yeah, my question is just about the best strategy. If you use approval IRV, then when you're deciding on which alternatives to put at your first rank, would it make sense just to use approval strategy?
I'm not sure. But I mean, I don't really, because we didn't investigate strategy too much, but I will say intuitively that IRV strategy might be closer. I don't know. Because you still eliminate candidates. I mean, a mix of the two, of course. But yeah, I think you cannot use like a full approval. I mean, if you really want to be strategic, you cannot be just approval or just IRV. You must do a mix, I think.
I'm curious to see which strategies work the best in general, but it just feels to me like approval strategy would work well, because if a strong majority could get behind one candidate that no other majority could overcome, then there wouldn't need to be any eliminations, or at least the eliminations would never eliminate that majority candidate, and they would just be pro forma.
But
So
there can be another majority candidate with even more support, because you can have several candidates with more than 50%. You don't,
Right.
What's different is in approval IRV, you don't stop when you have 50% for one candidate.
right. But
Because
if approval strategy centered in on a Condorcet candidate and that comes from the sincere preferences at least, then it just seems like at that equilibrium, everybody might be using a good approval strategy and just kind of ignoring the tricky parts of IRV strategy.
I see.
But that's just
maybe.
a guess. I don't know.
Yeah, okay, I see. So to investigate too.
Yeah, okay. Just curious.
Thanks for the
Okay, I think
Good
Clinton
idea.
has a question. Clinton?
So the fact that split IRV fails to satisfy these axioms is related to how you define the extension of the
So
axioms.
basically, can you find other axioms that would be in favor of split IRV? Can I, you always can find the right axiom. So is there an axiom? Can I find a way
Yeah.
to?
I mean, you can define the extensions of these axioms in such a way that the split IRV can satisfy the axiom.
So for clones, this is like the definition that is already defined in other works for weak orders. So it will be it makes sense to use this one.
Okay.
And for I think respecting cohesive majorities, I don't know if it's used in weak orders, but in other work on weak orders, but it's very similar to generalized PSC, which has been defined for multi-winner. So I mean, this was the most natural extension. Maybe you can find extensions that split satisfies, but I'm not even sure you can call them by these names, respecting cohesive majorities or being clone resistant to cloning.
Okay.
And monotonicity either, like, I don't think you can find I mean, monotonicity is different because it's not a generalization of an axiom that is satisfied by IRV.
Okay. Thank you.
But thanks for the question.
Okay, so we are already well, coming back. I don't know if someone already have some question about manipulation. We already had many questions. Clemens, maybe you wanted to add something, or Bill on manipulation? No, we have already said.
Bill and Dominic are discussing, I think.
Yeah, yes. I may have 1-2 comments of my own before perhaps we close. You're telling you in the title you say you have a characterization, axiomatic characterization of instance runoff, but it's not completely true because you don't use neutrality, anonymity, and some kind of unknown consistency. So is there any type of consistency axiom in the Young-Levengood framework or in that direction that one would be more could be invented to try to go a step further in the characterization? But that I guess it's hard.
So characterization of it among all scoring rules?
The whole structure of the weights, how you generate the weights. Usually you use the well, Dominic knows that, some people know that, you create a kind of consistency axiom in the Young sense, and there exist hyperplanes, so then the structure of the vector exists, and then you put your axiom to create the axiom. So you don't have an idea of a kind of separation axioms that would do the job. No, okay.
That will replace saying it's an elimination sequence rule?
Yeah, hereby it satisfies some kind of consistency axioms with neutrality and axiom, and with neutrality and anonymity, then the vector exists, and then they have this shape. No.
Yeah, no, it will be very nice. But I think if we have this, we also could have it for IRV, no? I mean, we don't have characterization of IRV,
probably. Okay.
That would be like super nice.
Another question by Bill?
Yeah, so
by Bill?
I just wanted to clarify. I was thinking of someone who wants to defeat a hated candidate. With partial orders, there's a new strategy, which is you place everyone else tied for first, right? And that, because you don't know which one of the other candidates is most likely to succeed in killing off your favorite one. Of course, the same strategy exists for approval voting, but it didn't exist for IRV until you allowed indifferences. And this could be an argument that says you are giving an unfair advantage by giving point to all your first place choices. Does that make sense?
By putting doing so you say the strategy is putting everyone first but one candidate?
Everyone but the candidate you want to defeat. You're not sure which. You couldn't do that before, and you're giving them each 1 point, so that's a powerful strategy.
Yeah, that's true. Yeah. That one strategy, but the question is like, is it bad? I mean,
well, it's an argument in favor of the people who say it's unfair to give all the top candidates 1 point.
Yeah, but that's a way of expressing your preference. Like you want everything but one candidate, so it's like your real preference. I mean, you can also say
it's a way of expressing it, but it gives a lot of power.
Okay.
Way of expressing it.
That's so you say that will be the argument.
Yeah.
That you need to answer. Okay. Yeah. Good point. Yeah. So thanks for the. Yeah, I think it's it gives power, but because it's power to express preferences, which is nice. It's not like over doing too much power, in my opinion. But that will be harder to explain, I guess, to people convinced of it.
Okay, so I think we should stop here. Maybe if there are other comments, you can directly talk with Dominic and Théo. I guess everybody has their emails. So we'll stop with 2 announcements. The first announcement is that we are closing today's 4th season of the COMSOC video seminar, and I'll be happy to announce there will be a 5th season starting in September. And the second announcement that I will make is that I'm here in the steering committee since the beginning. So today I will leave the steering committee, and I'm happy to welcome Clemens Pooper in the steering committee. We will be a new member of the steering committee starting in September. So thank you, Clemens, for taking the load. And I have to say now, happy holiday to everybody. And I will to some of you, we see you soon in 2 weeks in Paris for the result of the French election using plurality runoff. We'll see if plurality runoff is still the best rule in the world in 2 weeks from now in Paris. See you, everybody.
Yeah. Thank you. Thanks. Bye to everyone.
Thanks. Bye.